What we're going to look at today is to pick up the story that we've been involved in for quite a while now, of accidentally discovering that one's written a CrossCompiler. The first ever one I wrote, and I almost didn't realise I was getting into it. For those of you who've been following the story so far, I've been trying to motivate T diagrams as a way of understanding compilers in general, to illustrate the idea of moving compilers around or coping with hardware that won't talk to one another. We did before Arduino and Raspberry Pi, and we say everybody speaks very quickly to each other nowadays. Was it like that then? Not a chance. There wasn't a component, a universal component you could put in the middle that would bridge A to B in a very, very powerful way. For the infamous Linotype 202 jailbreak problem that we've covered a lot in videos, this was the one step before laser printers came on the scene. The trouble was that the 202 typesetter wanted everything down its own non-standard parallel port. What I had to do was to commission a single board Z80 chip. So fairly low level, character at a time stuff was coming down here. It was being sucked into the Z80 board as serial, because it was simpler, but output as parallel to be compatible with a parallel input port on the Linotronic 202 typesetter. I would point out that our bridging board here was hardly high tech. Steve Marchant, who built it for me, was a typical electronics engineer. You shouldn't be messing about with C, everything should be done in assembler. I'm being very generous with you. I'm giving you a 2K ROM to put your program text in. And if you can generate that out of C and not overflow, fine. But also, bless him, he did give us an absolute lifeline, which comes off the top of this diagram. He did provide a monitor port for a VDU if you're in the UK, VDT if you're elsewhere in the world, video display terminal, dumb terminal, just showing you the flow of characters into and out from. And that saved our lives many a time in debugging what was going wrong. The problem is that if you're going to put error messages out on the VDT, they have to be stored somewhere. He provided us very generously with 2K of RAM, riches beyond the dreams. So yes, the 2K RAM got very full, because I remember Julian, who took this project over from me, coming and saying, we would get on very well if only we could do without the error messages and the monitor. And I said, but we can't. So we phoned up Steve, who was not very sympathetic and said it was all due to our being computer scientists and not electronics engineers. And he'd given us a thing for very good reasons, where at the low end of memory was our 2K of RAM. Sitting on top of that was the 2K of ROM in the memory space, which was actually reading the characters, preparing them for parallel, listening for responses, all this kind of stuff. So when Julian and I said, can you give us more RAM? Do you know what he did? He gave us 2K more of RAM sitting on top of that lot. So our RAM holding was split into two. Never mind, said Julian, quite rightly. He said, we'll keep the lower level of RAM for the actual buffering of the characters. We'll keep all the error messages in the upper bit. He said, you know, frankly, we're only about 40 bytes short of what we need, but we have to have more. Anyway, we did our plod interfacing program, wrote it in C, but the Whitesmith's system reduced everything to assembler. So they had their own Z80 assembler. So you could do assembler inserts, and these could be linked in to your C-generated low-level code, all in one big happily family, but in the end it got united into a single big assembler level program, and you ran the assembler. You were scarcely aware of doing it, because by this time it was all packaged up into a shell script, and you just sort of ignored the detail and were happy for it to happen. Physically, what happened was you prepared your program, you turned on the PROM burner. It's a EEPROM. An EEPROM is a programmable read-only memory, electrically driven. You made a one-off effort and you burnt your program in there, and you took it off your target board, you plugged it in, you hoped it worked. If it didn't work, then there was an electrically erasable option to it, and you could reuse it. I don't know, I mean, eventually the thing would have got tired, but I don't think we ever had to use more than one, but anyway, that was the way it worked. So it was a physical transportation mechanism. You walked over, you put it in to the driver board, and you thought, this time I've got it right, it's going to work. Well, looking at diagrams like this, even at the time, I began to get sort of quite philosophical about this and think, well, you know, there's so many questions you could ask here. Here am I, sitting here producing my cross-compiled Z80 code, and it is cross-compiled because it's a different binary for the Z80 than it is on the PDP-11 where it's actually being produced. Wouldn't it be wonderful if only I could have far more memory for data and for program on that board? I mean, 4K may be enough for an electronics engineer, but really, let's get serious, it's pathetic. I also thought, well, we do this and we choose to come in an interface at the one character down a parallel port level. Now, we knew actually the Linotron 202 typesetter was front-ended, not by a PDP-11, but by another 16-bit mini computer. It was called the Naked Mini. It was made by a firm called Computer Automation. It was a 16-bit machine. Generally speaking, it was slower than a PDP-11 would have been, but it was adequate enough for the clunky electromechanical backing and forwarding of bromide that the 202 had to indulge in.
Linotype had bought in an off-the-peg sort of solution.
I think the reason that it was called the Naked Mini actually was that you could get a version with really no frills and furbelows, no case. It was a component you could build into a bigger system and all that, and everything you added onto was an extra, probably including the keyboard now in that lot. But you see, the more courageous attitude, which Bell Labs did, but they have, how shall we say, more experience, better skills and better lawyers than we had, is to say, blow this, that's not really a very good place to intervene. Why don't we mount an invasion and invade the Naked Mini and take it over completely? And that's what Ken Thompson did, of course, in the Great Jailbreak. Got himself on there. His favourite implementation language was the B language, which you remember, BCPL, B is the first interpreted language, still typeless. C came along, developed mainly by Dennis, but consulting Ken to be the system implementation language. So Ken's first reaction at getting Strange Machinery is, right, I'll look up how the assembler works, look up how the code is right down below, and overnight I will port my B interpreter and get it working on here. And of course, within a few weeks, it got absolutely everything in there working off his CrossCompiler, cross-interpreter and everything. And in many ways, that was the way to do it, because he could then decide, do I port the whole software mechanism onto that machine, or would I be better to say, I know enough now to drive it directly from the PDP-1144 and bypass that largely? So a lot of time was spent with his software decoding what the heck the 202 was up to in terms of rendering fonts, and it took a long time to figure out what they were doing with the characters and so on. So it still prompts the issue, do you invade the enemy territory, or do you stand off in the background and at arm's length using tongs just gently feed it the odd serial line character? And we just had to take that latter view. But with my thoughts about wouldn't life be easier if only I had a bigger Z80 memory? Could I actually host the compiler on that? Or would it be hopelessly slow? Yes, it probably would, but in theory, could I do it? Although it's an 8-bit micro and appeared, coincidentally or not, in the Sinclair ZX80, ZX81 around about that time, there was a lot of people asking, could we cross-compile stuff for the ZX80 and cross-compile it and run it? And at Cambridge at the time, there was a gentleman who will be known to many of you because he became famous in the Unix world, Steve Bourne. Steve Bourne is perhaps best known for writing the canonical Bourne shell, that comes as part of Unix. But before he took the job at Bell Labs, he was a PhD student and a researcher at Cambridge. And he wrote a system called Algol 68C, which is a dialect of the Algol 68 language. And his big aim, since Algol 68 was his baby, was, I can only imagine, because there's reports of these experiments going on, can I generate code on here for the Z80, and what is the best way for me to do this? So all these Z80 boards we're working with Clive Sinclair and his boys, you know, it would be lovely to be able to prepare lots of code for them. What's the best way to do this? Well, they had a great big IBM 360 machine, and what they discovered was their precious Algol 68 compiler, and they went through all the tricks we've covered in previous episodes of getting it to compile itself or getting it to compile a stripped down version of itself. What they found was that in the process of preparing that stripped down version, if I've got this right, the actual compiler itself had to get very big for a while in order that it could generate a smaller version that would fit on the Z80. And when you say, well, what's very big? 100K, and you're limited by the architecture on a Z80 to 64K. There's no solution. You had to cross-compile, yeah, and they did. But I think also, which is perhaps even more interesting, in fact, I went to see Steve at the time, and I don't know that I've actually seen him since. This really was in the very early 80s. I remember it well. I think he was back on vacation from Bell Labs. And he said, you know, the more you look at this business of transporting, or porting as it's now called, a compiler to a new environment, the more you realise what a mess we get ourselves into. We've got this language which gets compiled down close to binary on this machine. Then we want to do it on another machine like the Spectrum. And if we're not careful, we start all over again. So we must do the whole chain, must get everything ready and all that. But he said, you know, the hardest bit in writing a compiler is not all the syntax analysis and deciding what to do. It's actually doing it in the code generator against an environment that can often seem very, very hostile indeed. Wouldn't it be great if one could have a sort of assembler level, vaguely intermediate code that everybody could use? Now, he was one of the early people to realise this, and he said, and I've invented this thing called Z code. So my compilers now don't go to a specific binary in one step, they emit Z code. And then for the new machine, you don't have the whole big compiler to transport. What you're saying is the Z code is the back end, the syntax analysis, whatever, is the front end. All you need to do for a new architecture is write a Z code compiler or interpreter. I said, Z code? He said, yes, my new colleagues at Bell Labs want to call it Z code. And I keep telling them, I'm from the UK. It's my baby. It's Z code. This approach at the time became so well known and so discussed that it even had its own title, the UNCOL problem. UNCOL, I think it stood for Universal Computer Language. The forlorn hope was that it might emerge from all those doing compilers that there would be one superbly capable intermediate language which every single compiling system in the world could subscribe to and be happy with its facilities and so on. So the search for the UNCOL solution. Predictably, it doesn't work like that. There's always enough difference in architectures, and maybe even today, that it is not easy to have a one-size-fits-all. So I think this is a good place to draw a line for the moment and say we've got to investigate, how do intermediate codes work? How do they help you port a compiler from machine A to machine B? We vaguely see that it can obviously help because all you're having to write to get a foothold is an intermediate code interpreter for the new back end, and that gets you started.
your favourite computer shortcut key?
Oh, Control-C.
Control-C, because it just cancels things that I've done wrong.
Control-C, because it breaks my programs basically when they've got into the infinite loop.
Pixels squared, so 2 to 500 pixels squared usually. Training them takes a lot of memory. Once